Our subject this week is Network Protocol Deep Dive, and our first presentation is the Core Protocol Analysis. Starting right in, we go with the three-way exchange. The TCP Three-Way Handshake establishes a reliable connection before data transfer begins. This ensures both the client and the server can send and receive data while synchronizing their sequence numbers. The process breaks down into 3 steps. First, the client initiates the connection by sending a SYN packet. This sets the SYN flag to 1, generates a random initial sequence number, X, and sets the acknowledgement number to 0, since no data has been received yet. The client moves to the SYN sent state, and the server moves to the SYN received. Second, the server responds with a SYN ACK packet to confirm receipt and request its own connection. Both the SYN and ACK flags are set to 1. The server generates its own random sequence number, Y, increments the client's sequence number to X plus 1, and sends that back as the acknowledgement number. This confirms it expects packet X plus 1 next. Third, the client sends an ACK packet. Only the ACK flag is set to 1. The client's sequence number becomes X plus 1, and it increments the server sequence number to Y plus 1 for the acknowledgement field. With this final packet, both sides move to the established state and data transfer begins. Here we can see how this looks with the actual numbers. If the client starts at 1,000, over on this table here, if the client starts at 1,000 and the server starts at 5,000, step 1 sends a sequence of 1,000 and an ACK of 0. Step 2 responds with a sequence of 5,000 and an ACK of 1,001. Step 3 completes the loop with a sequence of 1,001 and an ACK of 5,001. In Wireshark, the interface simplifies these large random numbers using relative sequence numbers by default. It displays step 1 as sequence 0, step 2 as sequence 0 with an ACK of 1, and step 3 as sequence 1 with an ACK of 1. Mastering this sequence is critical because because disruptions to this flow form the basis of common network issues and security threats. If a client sends a SYN to a closed port, the server won't send a SYN to ACK. Instead, it responds with a reset flag, or RST, to reject the connection. During a SYN flood attack, an attacker sends thousands of fake SYN packets, but never returns the final ACK. The server eventually runs out of memory tracking these half-open connections in the SYN received state. To mitigate this, firewalls use SYN cookies. The server encodes this connection detail directly into its own sequence number Y, then forgets the request. It avoids allocating memory until a legitimate client returns a valid ACK in step 3, keeping the server online under pressure. Now we have TCP flag mechanics. TCP flag mechanics act as the binary steering wheel for the connection state. The standard TCP header uses a 20-byte base layer, and the control flags sit in the 12th and 13th bytes. The bit offset table shows how the modern 9-bit field works as a series of on and off switches, where 1 means the flag's active, and 0 means it's not. First are the congestion management flags. NS, or nonce sum, protects against packet concealment. CWR, or congestion window reduced, shows the sender received a congestion notice and reduced its transmit rate. ECE, or ECN echo, lets routers signal congestion without dropping packets. For data management, the URG flag marks urgent data that should be processed immediately ahead of everything else in the buffer. The ACK flag validates the acknowledgement number field, and it's required on every packet after the initial handshake request. The PSH, or push flag, tells the receiver to send data straight to the application layer instead of waiting for the buffer to fill. Finally, the state control flag means the connection lifecycle RC or reset abruptly drops the connection because of an error or a closed port. SYN synchronizes the initial sequence numbers when starting a connection, and FIN initiates a graceful teardown when a host has no more data to send. When tracking connections, calculating sequence and acknowledgement numbers depends on whether you're looking at control signals or actual payload data. The first scenario involves phantom bytes. Packets with only SYN or FIN flags set to consume one virtual byte in the sequence, even though they carry no application data. This allows the receipt to be tracked and acknowledged. In these cases, the next expected sequence number equals the current sequence number plus 1. The second scenario is a standard payload transmission. When a packet carries out actual data, the sequence number increments by the exact number of bytes in the TCP payload. The ACK flag itself doesn't consume sequence space, so the next expected sequence number equals the current sequence number plus the payload length. The raw Wireshark hexadecimal analysis at the bottom shows how to read these bytes directly. First, you locate the start of the TCP header in the final 4 bytes of row 0020. I forgot to add that. Here. Show you guys. Sorry, that wasn't. I forgot to take a screenshot. So here's the hexadecimal that I was talking about. You locate the start of the TCP header in the final 4 bytes of row 0020. So where 0030. There it is, right here. And this row here is the 0020. This is for the port information. 04D2 translate the source port 1234, and 0050 translate the destination port 80. Next, we skip the 8 bytes reserved for the sequence and acknowledgement numbers to reach row 0030 right here. The first field there is an A002. The letter A represents the data offset, meaning the header length is 40 bytes. The O2 translate the binary as all zeros ending in 10. Since that bit maps directly to the control flags, it confirms only the SYN bit is active, meaning this raw text stream is an initial connection request. Moving on to connection teardown and states. Closing a TCP connection requires a 4-way handshake because TCP is a full duplex protocol, meaning each direction of the data stream shuts down independently. The first table shows how this process unfolds across 4 steps. First, the client initiates an active close by sending a FIN ACK packet, signaling it has no more data to send. This moves the client to FIN wait 1 and the server to close wait. You can do that here. Second, the server acknowledges the request by sending an ACK packet with an acknowledgement number of U plus 1. This moves the client to FIN wait 2. During this stage, the server can still send any remaining outbound data. Third, once the server finishes transmitting data, it initiates its own close by sending a FIN ACK packet and moving the last ACK state to the last ACK state. Fourth and finally, the client acknowledges the server's FIN with a final ACK packet, setting the acknowledgement field to W plus 1. Once it receives that ACK, the server immediately transitions to close while the client enters a time wait. The time wait state is a protective hold pattern entered only by the side performing the active close. It serves two purposes. First, it guarantees final act delivery. If the final act from step 4 gets lost, the server will retransmit its FIN. The client must remain active long enough to send the ACK again, or the server remains stuck in last ACK. Second, it flushes delayed packets from the network so they don't interfere with a new connection, reusing the same IP and port numbers. This state is controlled by the 2MSL timer. This meaning the client waits twice the maximum segment lifetime. Since MSL is typically between 30 seconds and 2 minutes, time wait usually lasts between 1 and 4 minutes before the connection fully closes and the port is released. While a FIN exchange is a graceful shutdown, the reset flag is an immediate hard reset. The two tables in the middle highlight these differences. Starting with this guy here, a FIN teardown is a cooperative 4-step process that safely flushes queued data after security checks. A reset requires no handshake at all. It immediately discards pending data, bypasses the state machine, and forces the socket straight to close. This usually happens because of an application crash, a closed port, or a firewall block. In Wireshark, teardown anomalies can be identified through specific patterns. Filtering for TCP flags reset equals 1 helps identify hard failures. Large numbers of reset packets often point to port scanning, firewall rejections, or crashed application daemons. High close wait count means that the remote client already closed the connection and the server received the FIN, but the local application failed to close its side of the socket, usually because it's leaking resources or hanging on open connections. So at this point, this is just a little recap of what we just went over. And while anyone reads it, anyone who wants to read it, I have a question for you guys before we move on to the next section. Anyone can come off mute and answer this or answer in the chat. If you're analyzing a packet capture and see an unusually high volume of thin packets without any corresponding acts from the same source, what kind of activity or attack should you immediately suspect?
SYN flag.
Do you want to go into more detail about it, or anyone else want to? All right, move on then. So now we move on to the connectionless protocol. UDP is a minimalist connectionless protocol built for speed and low overhead. Unlike TCP, that operates without handshakes, acknowledgements, or flow control, because in real-time media, stilled data is useless data. The first table, comparing protocol flows, shows why this matters. When TCP encounters packet loss, it triggers retransmission. The receiver detects the missing packets, freezes the buffer, and holds all following packets. This is called head-of-line blocking, and it causes noticeable pauses in audio or video while waiting for the retransmit. UDP avoids this entirely. If a packet is lost, UDP simply drops it and immediately delivers the next packet, maintaining a continuous stream. Since UDP doesn't guarantee delivery, applications use 3 application layer techniques to hide packet loss from users. The first is forward error correction, or FEC. The sender includes redundant data alongside the original stream, allowing the receiver to reconstruct missing data without requesting a retransmit. This adds no latency, but increases bandwidth usage. The second is packet loss concealment, or PLC. If a packet is lost, the audio codec analyzes previous audio and generates a synthetic replacement sound to fill the gap, masking clicks or interruptions. The third is interleaving, shown in the second table. Instead of sending data chronologically, the application spreads fragments of frames across multiple packets. A normal packet loss removes an entire section of data. With interleaving, losing one packet only removes small pieces across several frames, making the glitch far less noticeable. These mechanics show up across three major use cases. In VoIP and SIP, call setup may run over UDP or TCP, but the actual voice payload uses RTP over UDP to keep latency below 150 milliseconds. For live streaming or web RTC platforms like Zoom and Google Meet, these rely heavily on UDP for low latency, peer-to-peer connection, dynamically adjusting video quality based on packet loss, much like what we're dealing with now. In multiplayer gaming, engines send player coordinates over UDP dozens of times per second. If position data from frame 12 is lost, it doesn't matter because frame 13 arrives immediately with updated coordinates anyways. So now we have UDP amplification attacks. UDP amplification attacks are a form of DDoS that exploits UDP's connectionless design and imbalance between small requests and large responses. This combination lets attackers turn low bandwidth systems into high volume traffic sources aimed at a victim. The first table shows the process in 3 stages. First, the attacker sends a very small request, often around 64 bytes, while spoofing the source IP address of the victim. Second, an open UDP service receives the request and acts as a reflector or multiplier node. Third, it sends a much larger response, often thousands of bytes, directly to the victim, overwhelming the target. For this attack to work, 2 key vulnerabilities must exist together. The first is IP source spoofing. Because UDP has no handshakes, packets are accepted based on header information alone. The attacker forges the source IP, so responses are sent to the victim instead of themselves. The second is exposed or misconfigured services. Many internet-facing systems still run legacy UDP services that respond to unauthenticated requests, giving attackers targets that produce large replies from small queries. The second table outlines common amplification vectors and their bandwidth amplification factor, or BAF. Memcache on port 11211 is the most severe, with amplification ranging from 10,000 times to over 51,000 times using simple GET requests. NTP on port 123 can reach about 550 times to 700 times using the old monlist command, which returns recent connection histories. SSDP on port 1900 reaches around 30 times using discovery requests, and DNS on port 53 typically achieves 28 to 54 times when using any queries or large TXT and security records. Defending against these attacks requires layered mitigation. First is source filtering, known as BCP38. Network operators use ingress filtering to block packets with spoofed source IPs that don't belong to their network. Second is disabling vulnerable features and closing exposed ports. For example, updating NTP to version 4.2.7 or later removes monlist, and restricting services like Memcache to localhost prevents public access entirely. Third is response rate limiting, or RRL. Servers monitor request patterns from the same subnets and throttle or drop traffic when abnormal spikes occur. Finally, scrubbing centers in Anycast networks help absorb attacks. By distributing traffic across multiple global data centers, malicious traffic is filtered and diluted before reaching the origin server. Security blind spots in UDP. The security blind spots in UDP mainly come from the way stateless firewalls treat packets in isolation. Since UDP doesn't have a handshake like TCP, a firewall can't reliably tell whether an incoming packet is valid response to internal traffic or unsolicited malicious data. To address this, modern systems rely on stateful inspection to simulate the connection model for UDP. The tracking table shows how stateful firewalls use tools like Linux contract to emulate this behavior. When an internal host sends an outbound UDP packet, such as a DNS request on port 50, the firewall creates a 4-tuple entry containing the source IP, destination IP, source port, and destination port. This marks the entry as expecting a reply and starts a short timer, usually around 30 seconds for UDP. If a matching response arrives within that window, it's allowed through. Once the exchange completes or the timer expires, the entry is removed from memory. While this improves control, it introduces several risks. First is the contract table exhaustion. Attackers can flood a network with UDP packets using randomized source ports. The firewall creates a state entry for each one, quickly filling memory and causing legitimate traffic to be dropped. Second is port spoofing hole punching. If an attacker knows an internal system frequently queries for a specific external service, they can spoof that service's IP and send malicious UDP traffic through the temporary state entry. Third is limited logging visibility. Standard firewall logs typically only include timestamps, IP addresses, and packet sizes. Since UDP has no connection teardown, there's no clear end-of-session signal, making it difficult to determine whether traffic was legitimate or malicious. To achieve better visibility without overwhelming infrastructure, security teams use several architectural approaches. The first is decoupled flow collection using tools like NetFlow or IPFix. Instead of relying on inline firewall logging, devices export lightweight flow data to dedicated collectors for anomaly detection without impacting performance. Second is deep packet inspection and protocol validation. Next generation firewalls, or NFGs, or NGFWs, inspects UDP payloads, not just ports. If traffic on port 53 doesn't match valid DNS syntax, it's dropped regardless of the state. And third is aggressive timeout tuning. Administrators reduce UDP traffic timeouts from around 30 seconds to as low as 10 seconds, and even lower for high-frequency protocols like DNS. This helps prevent state tables from being overwhelmed during scanning or flood events. And once again, we have a little recap here of what we just went over, some of the important topics. I'm going to ask another question if somebody else wants to answer this time. Question here is, since UDP doesn't use sequence numbers or a handshake, how do application layer protocols like DNS ensure that they're actually receiving a response to their specific request? Anybody have any guesses? Or any questions, Jimmy? So far. Right. So to answer real quick, this part trips people up because UDP is connectionless and doesn't use sequence numbers. To make sure the answer is legitimate, DNS relies on a transaction ID field in the header. When a system sends a query, it attaches a random ID number, and the responding server has to send the exact same ID back. Security teams also randomize the source ports now, so attackers can't easily guess the right combination and spoof the response. Moving on, we have ICMP abuse cases. Threat actors frequently abuse ICMP. While it's designed for diagnostics or error reporting, its stateless nature and default trust makes it a common target for bypassing security controls. This shows up in 5 main abuse cases. First is ICMP tunneling, used for data exfiltration and command and control or C2. Attackers embed arbitrary code inside the optional payloads field of type 8 echo requests and type 0 echo replies. This wraps non-ICMP traffic inside ICMP messages, creating covert channels that bypass basic port filtering. Detection usually focuses on unusually large ICMP packets, often exceeding the typical 32 to 56 byte payload, along with unusual bidirectional traffic patterns. Second is ICMP flooding, the classic volumetric DDoS attack. Attackers send large volumes of echo requests rapidly, forcing the target to generate echo replies until CPU and bandwidth resources are exhausted. Mitigation typically involves strict rate limiting at the network edge or blocking inbound ICMP traffic entirely where appropriate. Third, we have the Smurf attack, an amplification-based DDoS technique. The attacker sends echo requests to a broadcast address while spoofing the victim's IP. Every host on the broadcast network replies to the victim, multiplying the traffic and overwhelming the target. Defenses include disabling directed broadcasts on routers and using unicast reverse path forwarding to block spoofed traffic. Fourth is ICMP reconnaissance used for network mapping. This includes ping sweeps, where the attacker probes IP ranges with type 8 requests and watches for type 0 replies. It also includes TTL manipulation to trigger type 11 time-exceeded messages from routers revealing network paths. In some cases, attackers can also perform OS fingerprinting by analyzing ICMP responses with malformed packets, including TTL behavior and window sizing patterns. And finally, we have ICMP redirect attacks, which are used for man-in-the-middle positioning. A malicious host sends a forged type 5 redirect message, tricking a victim into believing a compromised gateway is the best route for traffic. This redirects sensitive data through the attacker's system. The primary mitigation is disabling acceptance of ICMP redirect messages at the OS level. So we have ICMP diagnostics. ICMP type and code fields work together to identify specific network failure conditions. The type field defines the general category of the message, while the code field narrows it down to the exact cause. Understanding these combinations helps diagnose routing MTU and connectivity issues without guessing. Type 3, destination unreachable, is the most important for everyday troubleshooting because it signals that a packet could not reach its destination. Code 0 means net unreachable, indicating a router has no route in its routing table for the destination network. Code 1 means host unreachable, which means a router can reach the network, but the final host is down or not responding to ARP. Code 3 means port unreachable, meaning the host is reachable, but no application is listening on the target UDP port. Code 4 means fragmentation needed, which occurs when a packet exceeds the MTU of a network link and the don't fragment flag is set, triggering path MTU discovery. Type 11, time exceeded, indicates a packet was dropped because it took too long to reach its destination. Code 0 means TTL exceeded in transit, where the time to live counter hit 0 before reaching its destination. This often indicates a routing loop and is also the mechanism used by traceroute to map network hops. Code 1 means fragment reassembly time exceeded, where fragmented packet pieces arrive too late or incompletely, causing the host to discard them. For basic connectivity checks, type 8 code 0 is an echo request ping. Type 0 code 0 is an echo reply confirming its reachability. Type 5 code 0 is an ICMP redirect, where a router informs a host that a better gateway route is available on the local network. The troubleshooting matrix shows how these map to real-world fixes. If you see type 3 code 4, it points to an MTU mismatch, so you would lower the MTU on the sending interface or fix filtering devices blocking fragmentation-related packets. If you see type 3 code 3, the service is not running, so you should check whether the application is listening on the target port. Repeated type 11 code 0 errors suggest a routing loop, requiring inspection of intermediate router tables to see in trace route output. And a type 3 code 1 points to a layer 2 issue, so you would check cabling, VLAN configuration, or the ARC table on the local network. ICMP smuggling and tunneling. ICMP smuggling and tunneling happens when an attacker abuses the optional data payload field in standard diagnostic messages to create covert communication channels. Because many firewalls and DPI systems treat ICMP as low risk by default, it can be used to quietly exfiltrate data or run command and control without opening traditional ports. The header structure shows why this works. According to RFC 792, an echo request or echo reply contains an 8-byte header followed by a variable length data field. This field was originally intended for simple testing like MTU checks or round-trip latency measurements. This is why common tools like ping use predictable padding. The key weakness is that whatever data is sent in an echo request must be mirrored in the echo reply. Since there are no strict rules for what the payload must contain, attackers can replace harmless data with encrypted commands, binaries, or stolen information. The second table illustrates full protocol tunneling. Malware can encapsulate higher layer protocols such as SSH, TCP, or HTTP inside ICMP packets. In this setup, the outer IP header contains the attacker's C2 address. The ICMP layer uses type 8 code 0, and the actual malicious payload sits inside the ICMP data select section. The infected host wraps commands inside echo requests, which pass through perimeter defenses because they resemble normal diagnostic traffic. The attacker's listener receives the packet, extracts the payload, and executes it, and returns results inside an echo reply. More advanced tools also abuse the identifier and sequence number fields, using them to track and reassemble fragmented data across multiple packets. This allows attackers to split large files into small chunks and exfiltrate them slowly over time, avoiding detection thresholds and data loss prevention systems. Since ICMP can't be completely blocked without breaking network diagnostics, detection relies on behavioral monitoring at the perimeter. First is payload inspection using pattern matching. Legitimate ping tools use predictable padding, so systems like Suricata and Snort can flag ICMP packets whose payloads don't match the expected signatures. Second is packet size analysis. Normal diagnostic traffic uses consistent sizes, so sustained streams with variable or unusually large payloads can indicate tunneling activity. And third is rate and ratio monitoring. Typical pings occur in short bursts, not continuous bidirectional streams. Long-lived ICMP, Type 8, and Type 0 exchanges to unknown external hosts are strong indicators of a covert channel or active C2 tunnel. Reconnaissance and mapping. ICMP reconnaissance lets attackers map live hosts, identify operating systems, and trace network paths before launching an exploit. Spotting these patterns early helps security teams shut scams down before they escalate. This breaks into three main techniques. First are ping sweeps, used for host discovery. Attackers often use tools like Nmap with the SN flag to scan entire subnets. The first table shows the process. Type 8 echo requests are sent rapidly across the range of IPs, such as the /24 subnet. Active hosts respond with Type 0 echo replies, while inactive hosts remain silent. The key signature is a high volume of requests across many destinations in a short time. A common detection rule is a single source contacting more than 10 unique IPs within about 1 second, or triggering alerts when 20 hits occur within a 10-second window. Second is OS fingerprinting, which is active system identification. Tools like Nmap with the uppercase O flag send deliberately unusual packets to observe how different systems respond. Attackers may send invalid ICMP types or malformed requests to see whether a host ignores them or returns errors like type 12 parameter problem. They may also manipulate IP options inside echo requests to test how the stack handles edge cases. Detection relies on response behavior patterns, especially TTL values. Linux and Unix systems often respond with TTL 64. Windows commonly uses 128, and Cisco devices often use 255. Analysts also look at the DF bit and other subtle IP stack differences. The main indicator is a single source generating a wide variety of unusual ICMP probes against one host. Third, we have traceroute probing for network path discovery. Tools like traceroute exploit TTL expiration to map hops along the route. The second table shows the pattern. Packets are sent to the same destination with increasing TTL values. When TTL reaches 0 at an intermediate router, it is dropped and a type 11 code 0 time exceeded message is returned. Once TTL is high enough to reach the destination, the host responds with type 0 or type 3 messages. A strong detection signal is a spike of type 11 responses from internal routers, which often indicates external mapping of network topology. Mitigation relies on three main controls. First is a strict rate limiting on edge devices to cap ICMP request volume per source. Second is filtering outbound type 11 time exceeded messages at the perimeter to reduce exposure of internal routing structure. And third is aggressive edge filtering, including dropping inbound type 8 echo requests unless explicitly required for monitoring or diagnostics. Little recap there for anyone who needs it. Anyone have any questions? And I also have a question for you guys again, if anyone wants to answer. All right, so many security teams completely block inbound and outbound ICMP at the perimeter network level. What are the pros and cons of doing this from an operational standpoint? All right. Well, The answer to that is you shut down a crucial enumeration set for attackers by blocking ICMP, which stops them from easily mapping out your network with ping suites. The downside is that you also break your own network diagnostics, making it a pain to discover new systems or troubleshoot connectivity. A good middle ground is keeping ICMP blocked at the outer perimeter, but allowing it internally, or using alternative management tools to track your assets. So we move on to the anatomy of a query. DNS resolves domain names through recursive and iterative name resolution. In a recursive query, the client asks for a final answer and forces the server to do all the work. In an iterative query, the client asks the server, and the server either returns the best information it has or refers the client to a better server. Consider a client at 192.168.150 visiting example.com using a recursive resolver at 10.0.0.1. Phase 1 is the client request, which is recursive. The operating system checks the browser cache first, then the system posts files. Post file. If the record is not found, the client sends a recursive query to the resolver with recursion desired or RD flag set to 1. The client then waits for a response or error. Phase 2 is the resolver lookup process, which uses iterative queries to walk the DNS hierarchy. The resolver performs this work itself. It sets RD to 0 on outbound requests, outbound queries. The packet flow shows the full resolution chain. First, the resolver queries the root DNS server. The root server does not return the final IP, but sends a referral to the .com top-level domain TLD servers, along with glue records. Next, the resolver queries the .com TLD server. It again doesn't know the final answer and instead returns a referral to the authoritative name servers for example.com. Finally, the resolver queries the authoritative name server, which responds with the actual A record mapping example.com to 93.184.216.34. Phase 3 completes the process with catching and response delivery. The resolver stores the results with its time to live so future lookups are faster. It then returns the final answer to the client with the recursion available, or RA, set to 1. The browser can then immediately begin a TCP handshake with the destination server. Every record stored on a name server is a resource record. Regardless of type, each one follows a standardized structure defined in RFC 1035. The first table shows the shared fields. Name stores the domain. Type defines the record format. Class is almost always in for internet traffic. TTL controls the time to live in seconds. RD length specifies the size of the data field, and RData contains type-specific payload. Here's how the main record types work internally. First are A and quadruple A records, which map to host names, which maps host names to IP addresses. An A record maps to a 32-bit IPv4 address and stores 4 bytes of binary data. A quadruple A record maps to a 128-bit IPv6 address and stores 16 bytes of data. Second, we have the CNAME record, or canonical name, which acts as an alias pointing one host name to another. Its RData contains the domain name encoded as a sequence of length prefixed labels. A key limitation is that CNAME can't coexist with other record types for the same name, meaning you can't combine it with records like MX on the same domain root. Third, we have the MX records, or mail exchange record, which defines where email for a domain should be delivered. Its R data includes a 2-byte preference value where lower numbers have higher priority, followed by the mail server domain. And fourth, we have the TXT record. Originally designed for human-readable notes, it's now widely used for machine-readable security data. This consists of a 1-byte length field, followed by up to 255 bytes of text per string, with multiple strings chainable for larger entries. This is commonly used for SPF, DKIM, and DMARC records. The comparison matrix highlights both structure and security risks for each type. A records can be abused in fast flux networks to rapidly rotate malicious IP addresses used for command and control. Quadruple A records may be used to bypass IPv4 only defenses through IPv6 channels. CNAME records are vulnerable to subdomain takeover if they point to decommissioned external services. MX records can be exploited for email routing abuse or spoofing if misconfigured. TXT records are often used for DNS tunneling, where attackers hide data inside text strings to exfiltrate information covertly. Exfiltration via port 53. Attackers abuse DNS for data exfiltration and C2 because many firewalls don't deeply inspect the content of port 53 traffic, which creates a major blind spot. The main abuse patterns fall into inbound C2 using TXT or CNAME records, and outbound exfiltration using heavily encoded subdomains. Normal DNS queries are short and predictable, while tunneling traffic is long, complex, and high entropy. You can separate legitimate traffic from malicious tunneling using 4 indicators. First is high subdomain entropy. Normal subdomains use readable words like mail or VPN. Tunneling subdomains use encoded data such as base 32, 64, or hex, which increases randomness and produces unusual character distributions, including mixed case and non-standard patterns. Second is extreme record length. Normal queries are typically under 30 characters, while tunneling traffic pushes closer to protocol limits. RFC 1035 constrains subdomain labels to 63 characters and full domain names to 253 characters, and attackers intentionally operate near those limits to maximize data transfer. Third is volume and frequency anomalies. Legitimate systems query a domain, catch the result, and respect TTL values. A system under DNS tunneling generates continuous, repetitive queries to the same domain to maintain a persistent data channel. Fourth, we have abnormal use of TXT, CNAME, and null records. TXT records are relatively uncommon in everyday browsing, but are heavily used in tunneling because they can carry up to 65,535 bytes of data and responses, enabling large payloads. Attackers exploit this to return encoded and even executable data back into the environment. Attack and analysis. Tunneling traffic often shows encoded blocks embedded directly into subdomains, frequently resembling base64 strings separated by dots. Decoding these can reveal stolen credentials or internal data being exfiltrated. Detection relies on multiple tools. In Wireshark, we can use flags that can filter unusually long DNS query names or requests specifically targeting TXT records. In Splunk, searches can target DNS query logs, filter for TXT or CNAME record types, measure query length, and highlight endpoints generating queries above a threshold such as 60 characters. And in SIM environments, Sigma rules can automate detection by alerting on TXT-heavy DNS traffic with unusually long query strings. While there may be occasional false positives from legitimate services, like cloud verification systems, this pattern generally is a strong indicator of active DNS tunneling. A little recap on this for anyone who wants to look over that. And while you guys do, if anyone wants to answer, if an attacker is using DNS tunneling to exfiltrate sensitive data, what specific anomalies or patterns would you look for in the DNS logs to catch them? So to answer that, when an attacker uses DNS to exfiltrate data, they hide the stolen information inside the queries themselves, which creates obvious traffic patterns. You'd look for a massive, unnatural volume of DNS traffic going to a single external domain. You'd also see unusually long, strange subdomains where data is encoded, along with high number of TXT or CNAME records instead of standard web requests. And on to our last section here. Stateless web requests. HTTP is stateless. This means that the server treats every request as an independent transaction. It doesn't retain memory of previous requests, so each one must include all information needed to process it. To simulate state in modern applications, systems use cookie, JSON web tokens or JWTs, and server-side session storage. Clients interact with resources using HTTP methods, which define the intended action on a URL. These methods follow two key rules. Safe methods only read data without changing the server state, while idempotent methods produce the same result no matter how many times they're repeated. The method matrix breaks this down. Get and head are both safe and idempotent. Get retrieves a resource, while head behaves the same, but only returns headers without a response body. Post is neither safe or idempotent. It submits data that typically creates new resources, so repeating the request can produce duplicates. Put is idempotent because it fully replaces a resource or creates it if it's missing, meaning repeated calls produce the same final state. Patch applies partial updates and is not guaranteed to be idempotent. Delete is idempotent because once a resource is removed, repeating the request does not further change the result. HTTP headers are case-sensitive key value pairs that carry metadata between client and server, grouped into three categories. Request headers describe the client. Host identifies the target domain and is required in HTTP 1.1. User agent describes the browser or client software. Accept defines acceptable response formats like HTML or JSON. And authorization carries credentials such as bearer tokens. Response headers describe the server and returned content. Content type specifies the format of the response body so the client can interpret it correctly. Content length defines the size of the payload in bytes. Server may expose software information and set cookies sends session data to be stored by the client. Control headers manage catching and security. Catch control defines catching rules across browsers and CDNs. E-tags provide a version identifier catch resource. Strict transport security forces browsers to use HTTPS only. And finally, HTTP status codes communicate the result of the request. They're grouped in 5 classes. 1, informational. 2, success. 3, redirects. 4 client errors, and 5 server errors. HTTPS isn't a standalone protocol. It's a standard HTTP wrapped inside cryptographic layer provided by TLS or Transport Layer Security. The layering model shows how this is structured. At the top is the HTTP application layer, which handles methods, headers, and payloads. Beneath that is TLS, which provides encryption, authentication, and integrity. Below TLS is TCP, typically on port 443, which ensures reliable delivery. At the base is IP, which handles routing across networks. Because of this stack, every HTTPS connection requires 2 setup phases: a TCP three-way handshake first, followed by a TLS handshake before any application data is exchanged. Modern HTTPS primarily uses TLS 1.3, which reduces handshake latency by completing key establishment in a single round trip. The workflow starts with the client hello message. The client sends supported cipher suites and includes a key share for its chosen key exchange method, effectively initiating the cryptographic negotiation immediately. The server responds with a server hello, selecting the cipher suite and returning its own key share. In the same exchange, it provides its digital certificate for identity verification and signals completion of its part of the handshake. The client then verifies the server certificate against trusted certificate authorities and combines both key shares to derive a shared symmetric session key. This key is never transmitted over the network. Once derived, both sides use it to encrypt all subsequent HTTP traffic, and secure communication begins immediately. Now we have protocol evolution. The evolution from HTTP 1.1 to HTTP 3 is basically a full redesign focused on one goal: reducing latency. The visible parts of HTTP, like methods, headers, and status codes, stay the same, but transport mechanisms underneath change completely. HTTP 1.1 is a text-based protocol that runs over TCP and sends data as human-readable streams. It's strictly sequential. A client sends a request and must wait for the full response before the next request on that same connection can proceed. This creates a major issue called head of line, HOL, blocking. If one request in the sequence is slow, everything behind it is stuck waiting. To compensate, browsers open multiple parallel TCP connections per domain, often up to 6, requiring its own handshake and competing for network resources. HTTP 2 solves this by introducing a binary framing layer between HTTP and TCP. Instead of sending full text messages, it splits communication into small binary frames such as headers, and data. Each frame is tagged with a stream ID, allowing multiple independent requests and responses to be interleaved over a single TCP connection. This enables multiplexing, where many streams share one connection without blocking each other. HTTP also improves efficiency with HPAC header compression and adds server push, which allows servers to send resources to the client proactively before they are explicitly requested. A little recap of the HTTP section. And while you guys look over that, if anyone wants to answer, I've got one more question before we move on to the quiz and conclusion. From a security monitoring perspective, when web traffic upgrades from HTTP to HTTPS, what visibility do we lose as offenders, and how do we compensate for that loss?
Sorry, could you repeat that again?
Of course. From a security monitoring perspective, when web traffic is upgraded from HTTP to HTTPS, what visibility do we lose as defenders, and how can we compensate for that loss? So the answer to this would be that the big challenge with HTTPS is the traffic being encrypted. So we lose the ability to see the payload of the packets. If an attacker is exfiltrating data, we can't analyze it directly. So to fix this, we have to rely on defense in depth. This means using things like TLS decryption proxies to inspect traffic, DLP solutions to alert on large data movement, and strict ACLs to block unauthorized sites completely. So in conclusion, these are the 5 core technical takeaways from the foundation of modern network architecture and defense. TCP handshake internals. TCP relies on strict SYN-ACK and ACK sequences. This isn't just a setup overhead. It's how both endpoints synchronize sequence numbers, establish shared state, and negotiate flow control parameters like window size before any real data begins. UDP removes the connection handshake entirely, which also removes built-in transport safety. Because of that, security devices like firewalls have to maintain short-lived pseudo-states using connection tracking to distinguish legitimate replies from unsolicited traffic, which is why UDP is heavily abused for reflection and flooding attacks. ICMP isn't just a diagnostic ping traffic tool. It's frequently abused for covert data channels, C2, and network recon. Attackers exploit payload fields for tunneling and use TTL-based error messages, like time exceeded, to map internal routing paths and topology. DNS normally follows a structured hierarchy of recursive and iterative lookups across root, TLD, and authoritative servers. In traffic analysis, high entropy subdomains, unusually large query names, and oversized text responses are strong indicators of tunneling or data exfiltration. And then HTTP is stateless and handles application layer logic through methods, headers, and status codes. TLS 1.3 then wraps that traffic in a single round-trip encrypted session, providing confidentiality, integrity, and authentication before any real application data is exchanged.